All right, hey everybody. So this is page 5, I believe. Again, I have no idea about page numbers, but it's question 10, and it deals with diffraction and interference. All waves, these are two properties that waves do that particles do not. So this is what kind of establishes the wave nature of light. Diffraction. Diffraction is the spreading out. So if I have a bunch of light waves kind of traveling in this way, when they hit this little opening, they're going to spread out in a circle and they're going to fill the room. It's why you can hear someone through a door, or sound's a great example of it, but like water waves will diffract around eddies in the ocean and things. That sounds the most thing, but light does it as well. Light bends around a corner. Now it doesn't bend as much um, as sound, but it does bend. So diffraction. And then if you have two sources of diffraction right next to each other, we can cause the interference of light. So we can see that property. It's not a lot of uses for this other than maybe measuring the size of a hair or certain things like that. But definitely not everyday uses. But we see it and we demonstrate it to demonstrate the wave nature of light. All right, so let's jump into it. Most of these are kind of theoretical or calculation. Key here, though, and I'm going to write it right next to it, is y equals wavelength times L divided by the distance between the slits. This is the equation. We can change all the different things and they affect how far apart the dots are. So you need to be able to do this. Now, this particular one, we are figuring out the thickness of a wire by shining a laser on either side of it and figuring out how far apart the maximums are. So that thickness is going to be D. So very thin wire, 640 nanometer red laser. Bright spots are half a meter apart. No, excuse me, you're half a meter from it, and they're 3 centimeters apart. So there's a lot going on with this. Again, the only equation, and again, this is going to come up later, that we don't convert nanometers is the energy of light. Everything else, we need to convert everything to meters. So for this one, determine the thickness of the wire. We have y equals wavelength times length divided by d. Remember, if I want to solve for d, I can swap it right here with y. So I get d equals wavelength times length over y, and so I can plug it in. So let's keep going. All right, wavelength is 640 nanometers. So that's going to be times 10 to the negative ninth, and that is times your length. That's 0.5 meters away, all divided by y, the distance between the dots. It says it's 3 centimeters there. So that is going to be 3 times 10 to the negative 2, or you could just say 0.03 if you know that meters. So that's all that. And then, what happened there? There we go. I clicked my picture. And then that's going to equal the distance of, or excuse me, the thickness of 1.05 times 10 to the negative fifth meters. That's very, very small. That's a thousandth of a millimeter. But that's all you need. You don't need to go much more than that. Okay. All right. If a green laser, so green has a changes the wavelength. That wavelength for green is going to be smaller than red. It's about equal to 490 nanometers. So how is that going to affect it? With the bright spots be closer together. So now we're thinking about y equals wavelength times length over d. Again, we just changed that wavelength. We made, use red here, we made wavelength go down. And since it's directly proportional, right, we're going to make y go down. And so they're going to be closer together. Right? That's that justification with that. So green laser is a smaller wavelength than that. All right. If the thickness of an even thinner wire were measured, so we got a thinner wire. Now we go back to red light. We're not changing wavelength again, so we're back to red. And so let's see. That's going to cause the thickness of the wire. That's going to change the D. The D is going to go down. And therefore, we're going to look at that y equals wavelength times length over d. Now, I'm going to use blue for this one. If I make d go down, well, that's on the bottom. That's an inverse And so Y is actually going to go up. So they're going to get farther apart. Farther apart. All right. And finally, if the screen is moved closer, I'm going to need a new color for that, aren't I? If the screen is moved closer, that's going to cause the L, the distance to the screen, to go down. And so we're looking at the same equation again. Wavelength times length over D. And now, let's change the blue to green. We'll do green. Now we're changing length to go down. Those are directly proportional. And so that's going to affect Y in the same way. So Y is also going to go down. And so we would say that it is closer together. Right? All right. Lastly, bright spots, dark spots. What's going on? We want to describe the different interference there. So bright spots are constructive interference. All right, constructive interference. And then the dark spots are what we call destructive because a crest is lined up with a trough. All right, and that is page, we don't know what page it is. That's page, we don't know what page it is. That's number 10.